On circular motion. I'm breaking circular motion up into two pieces. The first one is uniform circular motion. And what defines uniform circular motion? Yep, you looked in your notes. So uniform circular motion moves with a constant speed. And what do you call circular motion where the speed changes? Yes, very good. We're starting out with uniform circular motion. The math is just a little bit simpler. What does non-uniform circular motion have that uniform doesn't in terms of acceleration? Do you remember that? So in uniform circular motion, all the acceleration is centripetal. You can think of it as like all the acceleration causes the object to turn, to be in a circle. There's no acceleration making it speed up or slow down. In non-uniform circular motion, there's also tangential acceleration that's either speeding it up or slowing it down. So last time I gave you 6 steps for doing circular motion problems in general, except for there was one exception that I gave. Do you remember that? What was the? Looking at your notes is not remembering it. That's looking in your notes. And if I want you to do that, I'll say. So what's the? It's a certain kind of playground game. No. Tetherball, yeah, tetherball. So uniform circular motion, well, let's say I gave a general set of steps that holds for uniform circular motion and non-uniform circular motion. That you use for everything except tetherball problems. And tetherball does not just mean tether, it doesn't mean a tetherball necessarily. It means an object, a mass, swinging around on some kind of cable, and the only connection is that cable. So if you had, like here's an example, like you could have, say you had a dog sitting here with its tail going through a hole, and a person swinging from the end of the tail. That's fear. Okay, so this, for our purposes, is tetherball. That doesn't look very much like tetherball, but for us, I mean, it's a cable and a mass swinging in a circle, so that's tetherball. So what I'm going to do today is I'm going to do a couple of example problems. Let's see. I'm going to do one example problem, and then I'm going to give you the specific steps for tetherball problems, and then we'll do a couple more examples, and then non-uniform circular motion after that. Okay, so this is tetherball. It's different than you remember it as a kid. So here's the first example. Let's say that, so this is a post, and attached to this post is a string, and there's a ball on the end of the string, and the ball's moving in a circular path around the post. And let's say that it's supported on the bottom by a glass surface. So it's not just hanging from the string. So this isn't a tetherball problem.
So use glass to imply that it's frictionless?
Yes, that's right. Yep. Or ice or something. Yeah, exactly. And we have two questions. Well, first, let me give you the radius of this circle is 0.25 meters. Say the mass of the ball is 60 grams. And I chose that because that's the mass of the, we're going to do a lab that's sort of related to this, and that's the mass of the ball in the lab. And we want to calculate the tension in the string, given that the ball is rotating at 6 meters per second at a constant speed. So the first question to ask yourself in any circular motion problem is this a tetherball problem? Because that divides, divides into the two approaches to problems. This isn't, so we're going to use the method that I gave last time. So the first step in the method, anyone remember that? What's the first step? That's right. So first you have to choose a view, and what determines what view you take and what plane the coordinate system is in? So you need to choose a view where the circular motion can be seen as a circle. So if this is horizontal, which I guess it would have to be for this to work, the glass surface is flat, like on a tabletop. The ball's rotating in a circle this way. The view you have to take is either directly above or directly below. Those are the only two views you can take where the motion looks like a circle. Okay. I'm just going to, whenever we have that option, I'm going to always take a top-down view. There's nothing better about it, but I'm just going to always do it that way. So first step, choose the view and the coordinate system. So the coordinate system will go like this. The second step is we have to choose a point on the circle to do the calculation for. We have to choose one instant in the motion to investigate. Basically, we have four good choices for this. Where the circle meets the positive x, where it meets the positive y, negative x, and negative y. Anything else is just making it unnecessarily complicated for yourself. You'd have to use cosine and sine. Let's choose this point. Okay, so choosing the point was step 2. Step 3 is to draw the centripetal acceleration vector. What does that vector look like for this point? Yeah, centripetal means towards the center. So just go from the object toward the center of the circle. So that's the centripetal acceleration. And if you know the speed and you know the radius of the circle, you can calculate the magnitude. AC is always equal to the speed squared over r. So if it's 6 meters per second, that's 36 divided by 0.25. And so you get a total centripetal acceleration of 144 meters per second squared. That's the magnitude. And then we have to use the direction to give us the components of that acceleration. If the magnitude is 144 meters per second squared, what are the components? So remember, it's easy to do this step backwards. You're not trying to figure out the components of this point. You're trying to figure out the components of a vector directed toward the center. So you can think of putting the origin of the coordinate system at the tail of that vector. Your angle here would be 270. Or you can just eyeball it in this case, and it's going to be in the negative y direction. So the centripetal acceleration is 0, negative 144. Okay, so now we know everything we can know about the acceleration. It's uniform circular motion, so this is the total acceleration vector. So we know everything about the right side of Newton's second law. And now we can go back to the analysis of the left side of Newton's second law, which is what we've been doing since we started kinetics. Draw the free body diagram and write Newton's second law. So the free body diagram, the ball's up at the top of the circle. So there's a tension force this way. I'll just write that as T. What else is acting on the ball? This is always kind of a confusing aspect with these kind of problems. So what other forces are acting on the ball? I'm going to draw it bigger, actually. Yep, that's exactly right. So there are two other forces acting. So the tension's going that way. There's the weight force. And based on a top-down view, what's the direction of the weight force? Yeah, it's going straight into the page. And by the way, this is a common way of writing vectors into and out of the page that I'm not making up, other people use. It's like, imagine an arrow coming towards you. It would look like a circle and then a point in the middle. Okay, so that's a vector coming out of the page. And if an arrow was going away from you, you would just see the feathers. So the way you write that is a circle with an X. That's a vector into the page. Okay, so we would have a weight force going into the page with a magnitude of 0.5886. That's the mass times 9.81. And then we would have a normal force coming out of the page. We don't know the magnitude of that. Any other forces? So, you know, just like always, you're sort of mentally going around the boundary of the object, looking for contact with outside objects. But the only contact is that normal force and the string. Okay. Yep.
And it's just convention to do the vector in the ball, even though?
No, there's not really any convention for
It
that.
doesn't matter where you do it?
Right.
I'm really sorry, what's the 0.5886?
This is mg. So the mass was 0.06. All right. So now that's the free body diagram. Now we can write Newton's second law. The free body diagram gives us everything that goes on the left side. So we have 0, negative t. And now how do we represent the other two in our coordinate system? Well, the thing is, there's no way to represent them. Like, how do you, the question is, how far this way and how far this way do you go to make a vector that goes 0.5886 into the page? There's no way to go this way, you know, like, how do you, like, tell me the north, south, west, east directions to get to the center of the earth. There's no way, you know, and that's what the issue is here. So in our coordinate system, these two just don't even show up, okay? And so we just leave them out. If we were using three-dimensional coordinate systems, we could include them, but for us, we're just doing 2 dimensions, so they just don't even go in there. So the only force that shows up in Newton's second law is the tension force, and that's equal to the mass, 0.06, times the centripetal acceleration, which was 0, negative 144. And so if you calculate that, use the second equation, it gives you that the tension is equal to 8.64 newtons. How big is that compared to the tension force that would be on the string if the ball was just hanging there? What would the tension be if the ball's just hanging there? It would be, yeah, it would just be counteracting the weight, exactly. So it'd be 0.5886. So the bottom line is this cable tension can go up a lot as you increase the speed of a circular motion. Those centripetal forces that are making it move in a circle can be pretty big. That wasn't even moving very fast, you know, it was moving 14 miles an hour or something. Any questions about that problem? Yep.
I realize we're just doing this in a 2D, but if we were to do it in 3-dimensional one,
Mhm.
would that T change a lot, or is that pretty accurate?
No, it's accurate. It's 100% accurate. In 3D, it would look like this. The tension force would be 0, negative T, 0. The normal force would be 0, 0, N, yep, positive N. The weight force would be 0, 0, negative 0.5886. And those would be equal to the mass, 0.06, times 0, negative 144, 0. And so you just have 3 equations, and it would just let you solve for, just let you figure out that the normal force was equal to the weight force. But the other numbers would come out exactly the same. Any other questions? I'm erasing that. But you can see how similar 3D is to 2D, you know. The equations look just the same. The vectors just have one more component on them. Okay, so now let me give you the set of steps for tetherball problems. So in step 1 of the other method, we chose a coordinate system and a view where we could see the circular shape, right? With tetherball problems, instead take a side view. So if the object is following a circular path like this, take a view, and it doesn't matter which side unless, you know, the problem specifies something about that. But just imagine looking at it directly from the side. So, and then you can put your coordinate system right in the middle of the circular path at the height of the ball. And so what does the circular path look like for the tetherball? Yeah, the circular path is just, it's just a horizontal circle. And sometimes that can trip people up because you sort of feel like that cable should have something to do with the circle. And so people start to, you know, draw the circle up at the angle of that cable. But really the circular path just stays horizontal. Okay, steps 2 through 6 are the same. So the only thing different is that our coordinate system is going to represent a different view. So here's an example. Say that a ball supported by a cable travels around this circular path. Let's say that the radius again is 0.25 meters and the mass of the ball is 60 grams. And let's say that this angle is 45 degrees. We want to figure out two things. First, what's the tension in the string? And second, what's the speed of the ball? This is sort of an intuitive question. Couldn't this be going at any speed? So, like, how could I ask this question? Like, couldn't you make it go faster and slower? Or is there something in there that defines a specific speed? Yep. That is getting at it. Yeah, that is getting at it. There's sort of two. What the angle I think is sort of a clearer answer.
If it were going faster,
Exactly.
Angle...
So really, yeah, two things would change if you sped it up, right? So you had it going in this configuration, and then you sped it up. First, that angle would get smaller. It would get closer to horizontal, right? And then the second thing is the radius would get bigger because you'd have a smaller and smaller part of this cable that was going up, you know, that was vertical. Like basically, if you had this going 1,000 miles per hour, there'd be just a very little sag in the string, and the radius here would be almost the entire length of that cable. right now at 45 degrees, it's, I guess I could figure it out, but it's 0.25 times square root of 2, I think, something like that. And could you ever get it to be perfectly horizontal? Well, actually, no is the right answer, because if you do a free body diagram of that ball, there's a weight force. And so if the only other force on it is the string going perfectly horizontal, then no matter what the tension is in that string, it can't make up for that weight force. And so the thing couldn't be, Newton's second law couldn't be satisfied. Okay, let's solve it. So the view we're going to take looks like this. So there's the ball. I'll put the coordinate system here. What's the centripetal acceleration vector? What's its direction? It's from the ball toward the center of the circle, so straight horizontal. And we don't know the speed in this case, but we'll just represent the speed as like capital V, and then we'll end up solving for that later. So AC is equal to V squared over the radius. And 1 over 0.25 is the same thing as 4, so we can write this as 4V squared. And so in components, what's the centripetal acceleration? It's pointing in the positive x direction. Any questions about that? Okay, so it's going to be just positive 4v squared 0. And that's the total acceleration because this is uniform circular motion. So now we can go to the free body diagram. Yes, that's right. Yep, that's exactly right, and then it would be negative. The numbers would come out the same though. Let's do it that way. We can do it quick after we finish this one. Yep.
Can you explain how you got the 4v squared?
Yeah. So 1 over 0.25 is 4. So
oh, yeah.
Yeah. So that's how. All right, so the free body diagram of the ball. What's acting on the ball in this view? Yep. And this time the gravity is in our coordinate system. In fact, that's why for these tetherball problems, you need to choose a side view. So the weight is going this way. It's still 60 grams, so this is 0.5886. Any other forces or any outside objects touching this ball? Yep, the cable, and that's going this direction at a 45-degree angle. So Newton's second law, there's no normal force. That's only if it's, touching a flat surface, like sitting on, yeah. So in the other one, it was because of the glass surface, there was a normal force. So this angle is 45 degrees. So to calculate the components here, we have t times the cosine of 45, t times the sine of 45.
And the other reason you didn't draw the little place where the rope is attached?
Nope.
Do we need that consistency of the one without tension?
Yeah, as long as, I think at some point, you just start getting comfortable with what the tension's doing, and then you can stop making the little stump, yeah. Although if you keep doing it, when you're done, you can make it a picture of Cubert. Remember Cubert? No, you're too young. So this plus 0, negative 0.5886. I used to think I was great at Cubert, but I never cleared a board, so I probably wasn't really as good as I thought. The mass is 0.06. And the acceleration is 4v squared 0. So we can use the second equation. This says 0.7071 t minus 0.5886 is equal to 0. So t is equal to 0.832 newtons. So is that tension bigger or smaller than if the ball was just hanging there by the string? If it was just hanging there, the tension would be 0.5886. So it's a little bit bigger, not too much. Does that make sense? Would you expect? Yeah. So as soon as you start it moving, that tension starts to go up. And then the faster it moves, the more that tension goes up. Question? Yeah, that's right. And then now that we have t, you can plug that into the first equation. So you have 0.7071, that's the cosine of 45, times 0.832 is equal to 0.24 v squared. And so if you solve for v, you get plus or minus 1.57 meters per second. Do we want the plus or the minus? Plus, because we're looking for a speed, and that's always positive. So for this to have that 45-degree angle with the horizontal, it needs to be spinning at 1.57 meters per second. So now let's, we won't have to go through it as slowly, but let's go through the same calculation, but with the tether ball on the other side of the coordinate system. There are going to be some negatives in there, so I want you to see and make sense out of the fact that you'll get the same values, like you should, you know, because this problem didn't specify a specific point. So same problem. Choosing, let's say, a point in the positive x direction. So the view we're going to take is this one, coordinate system there. That's the point this time. So the centripetal acceleration now points this way in the negative x direction. The magnitude is still the same because the speed's the same and the radius is the same. So the magnitude is 4v squared. And since it's in the negative x direction, that means the centripetal acceleration is negative 4v squared 0. And now we can go to the free body diagram. There's the weight of 0.5886. The cable tension now goes this way. So Newton's second law, the weight force is 0, negative 0.5886. What's the angle now for this cable tension force? 135, yep. So now to come up with that angle, you'd put the coordinate system over here. There's the 180 line. This angle is 45 degrees. And so it's 180 minus 45, so 135. And so, well, I'll write that down. So t times the cosine of 135, t times the sine of 135. And that's equal to the mass times the acceleration. The second equation gives you negative 0.5886 plus 0.7071 t is equal to 0. So that gives you the same thing. The tension is equal to 0.832. And then plug that into the first one, and it says negative 0.7071 t is equal to negative 0.24 v squared. And so v, again, is equal to plus or minus 1.57 meters per second. You take the plus. So you get a negative from the acceleration and a negative from that tension force, and they cancel. Any questions about either of those? Let's do one more, like basically this exact same problem. Let's say that now we have it rotating around a circle like this, where this angle is 10 degrees. And let's say, so it can't be the same string because I'm going to say that this radius is the same. So the string would actually have to be shorter in this case than it was in the previous case for the radius to be the same. Let's say the mass is still 0.06 kilograms. All right, so think about this. What do you expect to happen with I gave you the angle. What do you expect to happen to the cable tension and the speed for this to work out? They both go up. That's exactly right. Yep. So let's take this view. The centripetal acceleration points this way. And it has a magnitude of the same thing it did last time, v squared over the radius. So 4v squared. The direction of the centripetal acceleration is in the positive x. So the acceleration is 4v squared 0. the free body diagram has a weight, 0.5886, and a cable tension, T. So Newton's second law says T times the cosine of 10, T times the sine of 10, plus 0, negative 0.5886 is equal to 0.06 times 4v squared, 0. What's the sine of 10 degrees? Okay, so 0.174 t is equal to 0.5886. So what do you get for t? So 3.3 newtons is the tension. And now we can plug that into the top equation. What's the cosine of 10 degrees? So 0.985 t is equal, we know t, is equal to 0.24 v squared. Can someone just give me that value of v? Okay, so v is equal to plus or minus 3.7, okay, 3.7 meters per second. We'll take the plus. So yeah, as the speed goes up, the circle gets, or the cable, I should say, gets more horizontal, and the angle, well, that's the angle. The circle gets more horizontal, and the tension goes up. Okay. Here's a problem I'd like you to work on. So let's revisit Carousel Kid. He's still on the carousel. Things are going pretty well for him. He still has a freakishly big head. No neck. Okay, so let's say that, okay, and he has a mass of 15 kilograms. Let's say that the carousel is moving this direction. His speed is 2 meters per second. The radius, so how far he is from the center of the circle that he's making, is 2 meters. And try to calculate two things. First, what's the acceleration vector? And second, what's the horizontal force vector that's required so that he doesn't slip? Okay. See if you can work through that one together. This is a side view, a top view. He's going, so he's sitting here like this, going this way.